Okay, why take from the top? Okay, because when we will calculate the moment, is equal to P multiplied by 0.05 plus E. And where is E coming from? Okay, E is this distance over here that I sketch out. So if this is our if this is our centroid, if this is our centroid, right? E will be the distance from here to here. That is our E. If you take it from the bottom, you have to compensate. Okay, if you take it from the top, it's easy. If you take it from the top, all you need to do is, so the load is 500. Is it 500? Let me see. The load is 400. Okay, the load is 400. Okay, multiply by 0.05. You can plus by 8.154 times 10 to the power minus 3. Okay. So this will give you the moment about mz is equal to 0.05 plus by 8.154 power minus 3 times by 400 is equal to 23.26 23.262 Newton meter. Okay, so this is centroid from the top. Okay, if we take mz centroid from the bottom, the answer will still be the same. But look at this, it's going to be 400 multiplied by 0.05 plus by 0.02, and then you have to minus by 11.846 times 10 to the power minus 3. Can you see that you have an extra step? And if you forget the extra step, if you forget to do this, okay, you are game over. Okay, so the answer will be the same. Okay, so if you take 0.05 plus by 0.02 minus by 11.846 power minus 3, then times by 400, the answer is the same. It's 23.262 Newton meter. Okay, centroid from the bottom. Okay, so for this case, you take it from the top. Okay, from the top. So you take it on the side of the applied force. Okay, so you take where the datum should be on the side of the, so the datum I'll write down here. Okay, so the datum should be on the side of the centroid. Okay, right. So for this case, we know that the formula that we're going to apply is equal to stress X is equal to positive Px over A. Okay, and then depend on whether is it tensile compression, we're going to have mz over izz multiplied by y. Okay, so we have calculated mz, which is equal to 23.262, izz. Okay, as I said, you all know how to calculate second moment of area now. I'm not going to do the working. I'm going to give you the magnitude, which is 3.88. 3.8802 times 10 to the power minus 9 meter to the power 4. And then the area will be equal, so the cross-sectional area will be equal to 104 times 10 to the power minus 6. Okay, so based on a cross-section like this, it's very straightforward how to determine the cross-sectional area. Okay, so by knowing those values, the next thing that we're going to do is we're going to calculate, we're going to determine what is our stresses at point A and point D. Okay. Anyone, any questions so far? Anyone?
For the IZZ and also
Area?
yeah, is it like we calculated using the method we learned in week 2?
Yeah.
Oh,
Okay.
thank you.
Okay. It's exactly the same. Okay.
Eugene, could you go over why we added 0.02 again for the centroid from the bottom?
This is because you are taking your datum at the bottom, yes or no? Right?
Yeah.
So you have to plus 50 and then you have to plus 20.
Oh, okay.
Then you minus back. Okay. So don't, I mean, you have to remember to minus back. As I said, I've been teaching this course. Probably this is the wait. I can tell you how many times I've been teaching this course. Hold on. I've been teaching this course 1, 2, 3, 4, 5, 6, 7 times. Okay. Students make that mistake. Okay, unfortunately. Okay. Okay. So anyone, any other question? Nope. Okay. So we are going to find stresses at point A and at point D. Okay. We're going to find stresses. So we're going to determine. So part A, we're going to determine stress X at point A and stress X at point D. Okay. So stress X, so we got the formula that we're going to apply. So we know that this is plus by Px over A. We know it's tension. This depending on where we're looking at or what we're looking at, mz over izz multiplied by y. Okay. So we try to, Px over A is the same for everyone or everything. Okay. So stress X at point A. Right. So this is equal, so the force is 400 divided by our cross-sectional area, which is equal to our cross-sectional area 3.88. No, sorry, our cross-sectional area is not 3.8, it's 104 times 10 to the power minus 6. Did I write that? Yeah, 104. Okay, so 104 times 10 to the power minus 6. Okay, so if we look at point A, okay, so our moment, our applied moment is in this direction, right? So this is our applied moment. So we know that this is compression, this is tensile. And we know where is our geometric centroid. So our geometric centroid is over here, right? So the distance from here to here is 8.154 millimeters. We know that. Okay. So from then on, so we know that this is compression. This side will be in tensile. So all we need to do at point A, it'll be in tensile. Okay, so this is going to be plus. Right, so our moment about Z, so we found our moment, which is equal to 23. Let me record 23.262 divide by IZZ, which is 3.8802. 10 to the power minus 9, and Y is 8.154 times 10 to the power minus 3. Okay, so over here you get 400 divided 104 power minus 400 divided 104 power minus 6. So the normal stress is 3.846 times 10 to the power 6 plus by 23.262 times 8.154 power minus 3, 3.8802 power minus 9 is equal to 48.884 times 10 to the power 6. Okay. So this will be equal to 3.846 plus by 48.884 is equal to 52.73 times 10 to the power 6 Pascal. So that is our stress at point A. And then the next thing that we're going to find is our stress X at point D. So the axial load is the same. Okay, so I'm just going to put in positive 3.846 times 10 to the power 6. Okay. Now D, at point D, right, the bending is going to induce compression. So minus. Okay, so 23.262. And then the distance will be 20 times by 10 minus 3 minus by 8.154 times by 10 to the power minus 3. So the distance from here to here now, from the centroid, right? So that is 20 minus by 8.154 is equal to 11.846 millimeters. Okay. And then divide by 3.8802 times 10 to the power minus 9. Okay. So this will be equal to 3.846 times by 10 to the power 6 minus by 11.846 power minus 3 times by 23.262 equal divided by 3.8802 power minus 9 is equal to 31.017 times 10 to the power 6. So this will be equal to 3.846 power 6 minus 31.017 power 6. It's equal to compression minus 67.171 times 10 to the power 6. Okay. So that is the force or the stress at point D. So you know that at point A is tensile, at point D is compression. So at a certain position, right? At your neutral axis, the stresses will be equal to 0. Okay, but because this is eccentric loading, right? The neutral axis position is not the same as the centroid. Okay, so we're going to find the shift. Okay, we're going to find the shift. So we're going to find the position of the neutral axis. Okay, so if you're going to apply the formula, you could. Okay, if we're going to apply the formula, we have stress X is equal to PXA over A minus by MZ over IZZ multiplied by Y. And you have to remember that this is what? This is minus. Yeah, you have to remember that. Okay. So then from here, you know, at the neutral axis, the neutral axis, as I said, is a stress field distribution. Stress X must be equal to what? Must be equal to 0. Okay. So this is equal to 0 is equal to PX over A minus by MZ over IZZ multiplied by Y. Okay. So you have PX over A, and this will equal to MZ over IZZ multiplied by Y. Okay. So if we are going to use the formula, okay, so Px over A is easy. Okay, it's equal to 3.846 times 10 to the power 6. Right. MZ, okay, so by looking at the moment, right? So if I'm going to draw the section again, I'm going to look at the section again. So AA Okay, at the line AA, where is the point of interest. Now some of you will say, Eugene, which moment are we going? What direction is the moment? Right. So we have to take the moment at AA, which is over here. Okay. So it's clockwise, right? So clockwise, so this will become the moment will be equal to minus now, right? Right. So because it's clockwise, the moment is negative. So now you have to minus moment about Z. So moment about Z is 23.262 divided by IZZ. So IZZ is equal to I forget what is our IZZ. 3.8802 times 10 to the power minus 6, and then you multiply by Y. Okay, so Y is the shift position, or is the actual position of your centroid. So Y will be equal to 3.846 power 6 times by 3.8802 power minus 6 divided by